Good afternoon. This is our narrated version of the Plate Tectonics PowerPoint. This could take a couple hours. In class, we will spend about 2.5 weeks on plate tectonics. All right, so plate tectonics is the most important thing in geology. We can refer to this as the unifying theory of geology. And what does that really mean? It means that plate tectonics is going to explain pretty much all geologic phenomenon. We have not always known how our planet works. So plate tectonics was not fully accepted until about 1968. It's actually a pretty young theory. So our opening slide here, you see there a map of the seafloor, and this is a little different than we're used to seeing. We usually see North and South America in the center. And this time we have Asia and Africa in the center. And what's cool about that is you can really see the mid-ocean ridges of the world. All right, so as you are watching this and hopefully taking notes, you're going to need to know that first bullet there. So I'm going to expect you to know the age of the universe, the Earth and solar system, and you don't have to know the age of the moon, but you are going to need to know how it formed. We're going to get to all that. So how old is the universe? These days we're saying about 13.7 billion years. So how do we know this? Well, there's a couple of things. One is just, knowing the speed of light and the distance light travels in 1 year, which we refer to as a light year. We search for the most faraway photons or light particles that we can find, and we can kind of extrapolate and say they've been traveling outward from the singularity for about 13.8 billion years. Well, astronomers also look for these things called globular clusters, which are the remains of the oldest stars, or the first stars that formed in the universe. And of course, we can also measure the Hubble constant, which is the expansion rate of the universe, and then extrapolate backwards to the Big Bang. So when I first started teaching here, which now has been 12.5 years ago, we were saying that the universe was 13.7 billion years old. So why has the age changed in recent years? And the answer is that astronomers have reason to believe that the expansion rate of the universe was actually a little bit faster very early in the history of the universe. So that's why we went from 13.7 to 13.8 billion. Okay, so question here. Do you think that the age assignment of the universe may change in the future if technology improves? Well, it already has, and it'll probably change some more. Okay, so this image here in the bottom right, this is one of many fabulous images that were taken with the Hubble Space Telescope. It is still working. It has far lasted beyond what they thought was going to be its lifespan. It will not continue working forever. It was definitely a worthwhile expenditure of money on the part of NASA. So what are those bright things in the image there? Okay, if you're thinking stars, well, you're not wrong. But the correct answer there is galaxies, and galaxies are made of stars. So as you look around at different ones, you might get an idea of the different shapes. We have spiral galaxies. You see at least a couple of those in there. We have elliptical galaxies. We have irregular galaxies as well. Does anybody know the name of our galaxy? I'll give you a hint. It's also the name of a candy bar. The Milky Way. Does anybody know what shape we are? We are a spiral galaxy. So this is an artist's drawing of the Milky Way, and astronomers have noted on this drawing approximately where our sun sits. So notice we are not in the center of the galaxy. We are in one of the outer spiral arms. That's a good thing. Okay, we're in a relatively safe spot. I'm really glad that our solar system is not closer to the center of this galaxy. Why? Does anybody already know the answer to this? Somebody will. Somebody in class always knows. We won't necessarily cover this in class. What lies at the center of every galaxy? The answer is a black hole. That probably makes sense because, what's scary or special about a black hole? Well, the gravitational pull is so strong that not even light can escape. So it might make sense that you would have to have something with a very strong gravitational pull at the center of your galaxy. Otherwise, why could you draw in so much material as to make 4 billions of stars? Okay, so the Milky Way is one of at least 100 billion galaxies in the visible in the visible universe, or the visible universe that we can see so far. And I've added a little something to this slide. I've heard anywhere from 50 to 100 billion galaxies, but actually recently I've heard that there can easily be more than 100 billion galaxies in the visible universe. So, how many stars are there in each galaxy? So our astronomers tell us that there's at least 100 billion stars in each galaxy. Okay, that's a lot of stars out there. What is the nearest galaxy to us? It's called the Andromeda Galaxy, 2.2 million light years away. The nearest star is pretty close, Alpha Centauri. It's only 4.3 light years away. Okay, so are we going to be sending a space probe to Alpha Centauri anytime soon? Well, who knows? There's only so much that NASA can do with the limited funding that they have. But if we were going to send a probe to Alpha Centauri, would it get there in just 4.3 years? Gosh, no. We don't have any kind of craft yet that can travel as fast as the speed of light. Here's the Drake equation, and I have to admit that I love talking about the Drake equation in class together, and I don't know that we'll have time for that during COVID, so we'll discuss it here. Okay, so the number on the left there, capital N, we're going to leave that alone for now. All right, so that is going to be our answer. And what does the Drake equation do? It's estimating the number of advanced technological civilizations, or ATCs, in any particular galaxy. So N star is the only number to the right of the equal sign that is going to be a large number. Let's leave that alone for now. FP, fraction of stars with planetary systems. When I was growing up, they didn't think that there were other solar systems out there. Okay, well, we've come a long way in astronomy, and we have found evidence for plenty of other solar systems out there. In other words, there are other stars that have planets around them, not just the sun. NE, the number of planets in a given system that are ecologically suited for life. FL, fraction of otherwise suitable planets on which life actually arises, because it won't necessarily arise even if the planet is suitable. FI, fraction of inhabited planets in which an intelligent form of life evolves. FC, fraction of inhabited planets with intelligent beings on which you get an actual advanced technical civilization. FL, fraction of planetary lifetime graced by an ATC. Okay, over on the right, let's take a look at the numbers that have been assigned to these things. FP, fraction of stars with planetary systems, 1/3. Okay. Maybe that's a little bit optimistic, maybe not. NE, number of planets in a given system that are ecologically suited for life. They're giving that a 2. Okay, that's pretty interesting. As of now, how many planets in our solar system have we found actual life on? And that answer is just 1, Earth. So that seems like an optimistic number to say 2. Perhaps someday we'll find evidence of past life, say on either Mars or Venus, but we haven't found proof of that yet. FL, fraction of otherwise suitable planets on which life actually arises, 1/3. FI and FC are kind of put together as one variable, and they're given that 1/100th. So that's a pretty small number. FL, they're also giving that a pretty small number, 1/100th. All right, so does anybody know when you multiply a bunch of small numbers together, what kind of answer do you get? Are you going to get a big answer, or are you going to get a small answer? And the answer is you're going to get a small answer. So if you just apply the Drake equation to just one star, say Alpha Centauri, then it's going to look like the chance for life elsewhere, or advanced technical life elsewhere, is impossible. But the key here is that you're going to take that really small number that you get and you're going to multiply it not by one star, but by, gosh, at least 100 billion stars. And that's just looking at one galaxy, say just the Milky Way. So when you look at it like that, maybe it's not so impossible. So here we have our little gray alien on some other planet teaching a college class using the Drake equation. They're looking for us and we are looking at them. Oh, and look, that's a chalkboard with chalk. Well, that's old times. Using a sedimentary rock to write on a metamorphic rock in a math class. Okay, how old is the Earth? Well, you're going to need to know how old the Earth is, how old the oldest continental rock is, and how old the oldest oceanic rock is. So the Earth is approximately 4.57 billion years old. How do we know that? Well, we'll get to that. So the oldest continental rocks are about 3.96 billion years. Notice there's an age discrepancy there. So why do we insist that the Earth is 4.57 billion years old when we only find the oldest rocks that originated on this planet to be 3.96 billion years? There must be some other object that we find that gives us a radiometric age date of 4.57 billion years. And what would that be? Well, you guessed it, meteorites. So meteorites give us that age date of 4.57 billion years. So that age is good for not only planet Earth, but the entire solar system. Now, how about the oldest oceanic crust that's currently found in an ocean basin? That rock is a lot younger, only 180 million years old. So there's a big discrepancy there, isn't there? We might say that oceanic crust does not make it into old age. Why not? Well, we're going to answer that later in this unit. Here we're looking at pictures of a couple of meteorites. On the left is an iron meteorite. On the right is a stony meteorite. We also have combinations that are referred to as stony iron meteorites, and then we also have carbonaceous chondrites. If you go to the Smithsonian Museums in DC, and you go to the Museum of Natural History, which is the Science Museum, as you're somewhere down on the first floor and you're going through and looking at awesome minerals and rocks, they have not only a sample of the Acasta gneiss, oldest rock, 3.96 billion. They have the Acasta gneiss, a big sample out in the walkway so you can put your hands on it. They also have some very large meteorites in the walkway that you can put your hands on. Carbonaceous chondrites are interesting. So no, you're not going to have to know the types of meteorites for your third exam. Carbonaceous chondrites are worth mentioning though, because they're the most rare type of meteorite. And what's really interesting is that they have organic material, including simple amino acids. Okay, age of oceanic crust. This is an image I like to show in class. We'll have to see which slides we have time for. But what I want to point your attention to is that what's important on this map is the oceanic crust, not the continents. The continents are in yellow and you can just leave them alone. So you see there that the ages, it's color coded. So if you begin on the left in the red, that's your very young oceanic crust. And then as you move to the right and you get eventually to a darker green, you're going to get to Jurassic age oceanic crust. So I want you to look at the Atlantic Ocean, North and South Basin. Where in the Atlantic Ocean do you find the youngest crust? Everybody see that it's there in the middle? And then the crust gets older on either side as you move away. Well, why do we have the youngest oceanic crust in the middle of the Atlantic? And the answer is because the Mid-Atlantic Ridge is there. And that's where plates are moving apart and melt is creating brand new oceanic crust, basalt. All of it is basalt, by the way. Okay, the Big Bang Theory. It wasn't just a cute TV show that has unfortunately since finished its run. So, the physicists, astronomers, tell us that the universe began, again, roughly 13.8 billion years ago, with something we refer to as a singularity, or all matter in the universe squeezed into one infinitesimally small point. So the Big Bang refers to the cataclysmic explosion that sent this matter into space and began our universe as we know it. And this material started expanding and is still expanding. Our universe is expanding today. So think about, we just discussed that there are at least 100 billion stars in each galaxy, maybe as many as 300 billion in each galaxy, and there's probably at least 100 billion galaxies out there. How do you get all that material into one tiny point? So it might help to mention that astronomers think that way back then, in the beginning of the universe, that we only went up to number 4 on the periodic table of elements, up to, say, beryllium. So that might make it a little bit easier to wrap your head around. So what did it take to form all the other elements, including the much higher proton number elements that we have, say, here in our solar system? And that answer is it took supernova explosions. That's just one means by which stars can die. What did the Big Bang look like? Well, we don't really know a big explosion. This is an artist's idea of what it might have looked like. So the solar system, not just the Earth, is approximately 4.57 billion years old. So we're briefly going to talk about nebular theory, or how stars form. So stars form from nebulas. What is a nebula? It's a swirling gas cloud. So our nebula was mostly hydrogen and a trace amount of helium. Okay, so how do you form a star from that? Well, gravity. You get molecules of hydrogen coming together and accreting, and you eventually are going to form a protostar out of this hydrogen. Now, the star didn't always burn bright like it does now. That wasn't going to happen until fusion started in the core. So it took some time for these hydrogen atoms to come together from the nebula to form a protostar, and for it to finally get big enough that there would be so much pressure towards the center that fusion would begin. So how does the sun burn and give us light and energy? And the answer is the sun is basically a giant nuclear reactor, and it's fusing hydrogen, one proton, into helium. So you take 2 hydrogen and fuse them to make a helium. And of course, every time this happens, it's releasing a heck of a lot of energy. So here we're looking at, there on the left side, that's an image from the Hubble Space Telescope. That is the Eagle Nebula. Isn't it beautiful? Incredibly so. Okay, so over on the right, you've got kind of a step-by-step drawing of how do you go from one of these nebulas into a protostar. So this nebula here on the left, Eagle Nebula, will likely become a star in the future. If you want to pause on this slide and read about it, you can. Basically, it's, and there should be something, well, I know there is something in your textbook about how supernova form these higher proton elements. So this is a nice step-by-step drawing here, going from our nebula to the solar system as we see it today. So our star is anywhere from a 2nd to 5th generation star. We know it's not a 1st generation star. We don't really have any 1st generation stars that are still stars. They have burned through their fuel and died. So this is just kind of a neat little drawing here, just showing accretion of hydrogen forming our protostar. What kind of material accreted to form the planets? Well, there were rocky materials forming the inner planets, and then gases and frozen gases forming the outer planets. Okay, so basically your rocky particles, what we might refer to as space dust, were captured closer to the sun in the sun's gravitational field. Gases and frozen gases were still captured in orbit around the early sun, but the solar wind was able to blow those lower density elements out to the further reaches of the solar system. So the more dense materials form the terrestrial planets, also referred to as the inner planets, Mercury, Venus, the Earth, Mars, and also the asteroid belt, which is in between Mars and Jupiter. And then your less dense materials, gases and frozen gases, form the outer planets. Jupiter, Saturn, Uranus, and Neptune. Hey, what happened to Pluto? When I was a kid, Pluto was a planet. Well, Pluto's not a planet anymore. What happened? We'll talk about it on another slide. This is a nice image here. It's pretty good at showing the relative sizes of these planets and what they kind of look like, their colors. It's not so good at showing how far apart they are. That's okay. We kind of need to scrunch this stuff together to get it to fit on one slide. Okay, so you have there Mercury through Mars, your terrestrial planets. Ceres is a dwarf planet within the asteroid belt. Then you get the outer planets, the gas and frozen gas planets like Jupiter, Saturn with the rings, Uranus, and Neptune. So Pluto was the 9th planet for a long time. Back in 2003, astronomers discovered a new object out there. And we had to either add a 10th planet or change the definition of planet. So we changed the definition of planet. So first of all, Pluto, its moon, I don't know if that's Charon or Chiron. The moon is almost as big as Pluto. It's also going to have its own weird orbit. We'll see that on an upcoming slide. This is a different way to show the planets, and in this case, they're concentrating on what elements are making up the planets. So let's begin with the terrestrial planets first. Silica and oxygen. You guys remember the silica tetrahedra? And SiO2 quartz. If you take then some metals and add them to the silica tetrahedra, you get a lot of our silicate minerals, which have built most of this planet. So basically, minerals, hard materials, have formed the inner planets. The outer planets are made of hydrogen, helium, ammonia, methane, hydrogen sulfide, water vapor, carbon dioxide gas, and noble gases. Here we are looking at the orbits of the planets, and you notice that every planet but Pluto is going to orbit the sun basically within the same plane. And then you have Pluto and its large moon kind of doing their own thing. No wonder they took Pluto out. And then this is another image of our solar system. This one is maybe a little bit better because it's a little further out and it's including the Kuiper belt. And what they're not showing here is the Oort cloud. So we might say the Oort cloud is kind of the outer reaches of our solar system. Okay, so how did our beautiful planet Earth formed? So these rocky particles, space dust, that were trapped in orbit around the early sun, these particles came together with gravity, and they formed planetesimals, or planetary accretionary disks. So through accretion in this case just means the growth of planets, you have more and more dust particles brought in by gravity smacking onto your planetesimal, until they grow into the size that they are today, and there's just not that much material out there left to accrete on. And then, of course, the outer planets, gas and frozen gas planets, formed in a similar manner, but it was accretion of gases and frozen gases. Okay, so what might that look like? Well, who knows? I think this image on the top left is pretty good. You see over there on the left our early star, and then you see accretion happening, what's going to eventually build an Earth. Now look at that image in the bottom right. I like to show this one in class, although we may not get to do that this semester. Does that look like a place that would be hospitable for life? Gosh, no. So that's early Earth. Maybe it'd been around, 500 million years. It was old enough that the moon had already formed. We'll talk about that on an upcoming slide. But what you see is you don't see any water. No evidence of life. You see that dark crust there. We're pretty sure that the first crust that ever formed here was oceanic. But that crust was just destroyed and recycled many, many times. And you see that our young Earth here is being bombarded quite heavily with meteorites and more material accreting onto our young planet. So the Earth has layers, and that is the subject of one of our 3 video lessons for plate tectonics that we have on Canvas. We will still talk about it here in this narrative PowerPoint though. Anyway, so shortly after Earth formed, it began to differentiate into layers, and that was based on the density of materials. You can stop and read through this if you would like regarding the differentiation of Earth. Okay, formation of the moon. Potential extra credit question here on your 3rd exam. Shortly after we think we formed a rudimentary core and mantle, Earth was hit by a small planet-sized body. Imagine Earth getting hit by something the size of Mars. Wow, that's just crazy. Okay, so 2 things happen here. One is that some of this material from this planet-sized body actually accreted onto Earth and made it bigger, and that was potentially a good thing for life on this planet, because if this had not happened, Earth would be smaller, and maybe we would not have had a strong enough gravitational pull to keep our atmosphere and surface water from escaping after they formed. But some of that debris was ejected outward and then was captured in orbit around planet Earth and then accreted to form the moon. Here are a couple of drawings to show what that might have looked like. By the way, that image on the left, they're not using blue very well. They're not using color very well. Okay, that should probably be an orange or a red. That is not trying to say that we had water here at that time. We're pretty sure we did not. This is a nice step-by-step drawing here, going from our nebula on the top left to forming a protostar, and then accretion forming the planets like planet Earth. You see there on the middle left, planet Earth with a core and mantle formed, and then we get hit by that small planet-sized body, and that material will eventually accrete and form the moon, and of course the size of Earth has also increased. Here we're looking at an image of the moon. By the way, you probably already know this, but the moon rotates so slowly that it pretty much keeps up with the same face looking at the Earth as it is in orbit around the Earth. In other words, we always see the same side of the moon. That's why there is a phrase and an album called Dark Side of the Moon. What do you see here? You see those dark patches? Those are referred to as seas. One of them is called the Sea of Tranquility. Now, have we found any liquid water on the moon? And the answer is no, we have not. Why do they call these things seas? It must be because these are ancient basalt flows. Now, it's quite likely that these basalt flows happened due to melt that occurred as the moon was getting bombarded. We're not saying that we see necessarily evidence for volcanoes or plate tectonics on the moon. And of course, you see a lot of craters. And the craters on the moon are really quite old, but you still see evidence of them because you just don't really have weathering on the moon. like you do here on planet Earth. Okay, radioactive decay. We'll very briefly discuss this here in our PowerPoint. I can tell you now that we will not have time to do this in class. 3 basic types of radioactive decay, and this is never on your exam anyway, but I do want to at least mention it because some of you might end up taking Earth history in the spring. This will give you a little bit of background. So radioactivity is referring to spontaneous changes or decay that occurs in the nucleus of atoms that are unstable or radioactive. So one type is referred to as alpha emission. Okay, so what happens here is that 2 protons and 2 neutrons, also referred to as an alpha particle, are ejected from the nucleus. I have in parentheses here helium atom. It's not exactly a helium atom. It's similar. It's the same number of protons and neutrons, but a helium atom is going to have some number of electrons. Anyway, so when you eject this alpha particle out of the nucleus, you're going to reduce the atomic number by 2, meaning that you've lost 2 protons. That means you now have a completely different element here, something different than you started off with, and the mass number will be reduced by 4. Beta emission, what happens here is that an electron, also referred to as a beta particle, is ejected from the nucleus. And you might be thinking, wait a minute, what is an electron doing in the nucleus? It doesn't belong there. Well, you're right, it belongs in the orbital shells around the nucleus. What happens is within the nucleus, you have a neutron turned into a proton and an electron. The electron does not belong, it is shot out from there. So what happens is that the atomic number now increases by 1 because you've added another proton. So again, you have a completely different element than what you started with. The mass number, however, will remain unchanged. And then there's electron capture and decay. What happens here is that an electron can be captured by the nucleus and then combined with a proton to form a neutron. So it's kind of like that beta emission in reverse. What happens here is that the atomic number is going to decrease by 1, so yet again you have a completely different element than you started off with. But in this case, the mass, atomic mass or atomic weight will remain unchanged. So some terms here you hopefully are already familiar with. The parent material is the unstable radioactive isotope that you begin with, like say uranium-238. The daughter product is the stable isotope, the final isotope, that the last thing it will become on its path of decay. That is the daughter product. So in the case of uranium-238, the daughter product is lead. I can't remember if it's lead-206 or lead-207 because there's also a uranium-235. But uranium always decays to lead. Uranium is the parent, lead is the daughter. The half-life is the time it takes for half of the parent's material there to decay into the daughter material. So how do we have these ages on these very old rocks and meteorites and moon rocks and rocks in the Grand Canyon? Well, radioactive dating. So what happens here is that we have measured the half-life of all the radioactive pairs that we have on this planet. So what you do is you use something called a mass spectrometer, and that is going to give you a ratio of parent atoms to daughter atoms, and then knowing the half-life, you can calculate the age within some narrow margin of error. This is the radioactive decay curve. You'll notice it's not linear, not a straight line. So over there on the top left, you start with, say, brand new igneous rock. You just have had a rock crystallize in a shallow intrusion. So you begin with 100% of the parent isotope, we'll say uranium-238. So there, after time 1 half-life, you now have half and half. After a second half-life, you now have only 25% parent atoms, but you have 75% daughter atoms, and so forth. So these are some radioactive parent and daughter products that are very useful in radiometric age dating for geology. Let's look at some of these half-lives. Okay, uranium-238 to lead-206, 4.5 billion years, or almost the age of the solar system. Uranium-235 to lead-207 is much shorter, 713 million years. Thorium-232 to lead-208, wow, that's almost the age of the universe, 14.1 billion years. Look at rubidium to strontium. That's a very long half-life, 47 billion years. You might think that the rubidium-strontium pair would not be useful because we're nowhere near even one half-life occurring, but it actually is a useful radioactive pair in radiometric dating. And then potassium to argon is 1.3 billion years. I believe potassium to argon is especially useful in dating fine-grained igneous rocks, as in, extrusive igneous rocks like basalt or rhyolite. Here is a very generalized geologic timescale. Now, sometimes in class, we spend maybe 5 minutes on this. We'll just briefly go over this in our PowerPoint here. If you want to learn more about the geologic timescale, you should come back and take Earth history in the spring. Anyway, just some interesting things here. So the Precambrian goes from 542 million years ago all the way back to the beginning of planet Earth, 4.57 billion. It's divided up into two different periods, the Archean and the Proterozoic. So why do we make, well, first of all, you see there that a significant proportion of Earth's history is in the Precambrian. You might think nothing important happened in the Precambrian, and that's not completely true, but we do make a distinction at about 543 million years, and we go from the Precambrian into the Cambrian and Paleozoic because of something referred to as the Cambrian explosion, where we saw a great diversity in the life forms. Okay, so Cretaceous, the Carboniferous, which is divided into Mississippian and Pennsylvanian, that's where you get a lot of coal swamps. Paleozoic, by the way, I like to think of that as the age of trilobites, or just simply the age of invertebrates. Mesozoic is known as the age of dinosaurs, Triassic, Jurassic, Cretaceous, when the dinosaurs lived. And then the Cenozoic, we like to think of as the age of mammals. So in this slide here, we see just some significant milestones. So we definitely had life prior to the Cambrian. I think our oldest undisputed fossils are at about 3.5 billion, single-celled, of course. Anyway, so you have the Cambrian explosion, you start to get your first fish, your first chordates. The Devonian is kind of known as the age of fish, and you start to get a great diversity in fishes that have jaws. You get your first amphibians then. By the way, your first reptiles appear in the Pennsylvanian, which is part of your Carboniferous. There's a very major extinction at the end of the Permian. As a matter of fact, it's the worst mass extinction ever in Earth's history. In the Triassic, you get not only the first dinosaurs, but also the first mammals. You get the first birds in the Jurassic. Who did the birds evolve from? Hopefully you've heard this before. They evolved from dinosaurs. You get your first primates in the Cretaceous. At the end of the Cretaceous, you have another mass extinction event, and the dinosaurs go away, paving the way for mammals to flourish. Okay, breakdown of Earth's layers. This is a very rudimentary drawing, so we will look at an upcoming slide and discuss this more. There is a video lesson on the interior of the Earth that I expect you guys to watch. All right, so here we are looking at a pie slice. So imagine it's like a piece of pie or a slice of pizza, sort of, or better yet, imagine a melon and taking a core of that melon. This is kind of what it would look like here. So we're going to begin down at the bottom at the point. Okay, we've got the inner core, then we have the outer core, then we have the mantle, which is the thickest layer. You're not going to have to know the thicknesses of these layers or the depth to these different transitions. We'll discuss these layers in a little more detail on upcoming slides. So the mantle, there's different parts to the mantle. So you'll notice kind of towards the top of that pizza slice, you have a dashed line there and it says upper mantle. There you're going into the asthenosphere mantle. Now there's a yellow arrow showing a blown up portion of the top, as in closer to Earth's surface, there on the top left. So the asthenosphere, it's shown in orange, and that is just to represent heat. Okay, it might look like magma. It's not. It's actually not molten, but it is going to behave like a plastic. Okay, and then you have your lithosphere or lithospheric plates on top. And you see there that you have, well, there's this thing there called the MOHO, the MOHO. That is going to be our crust / lithospheric mantle boundary. So the crust is on top. You got two basic types. You got continental crust, which is granite. You got oceanic crust, which is basalt. So the bottom part of the plates, the thicker part of the plates, is referred to as the lithospheric mantle. And these lithospheric plates are going to move together kind of in a rigid or rocky manner, moving across the plastically behaving asthenosphere. And in the bottom left there, you see in our image of the scales that oceanic crust is more dense than continental crust. Oceanic crust is basalt. Continental crust is primarily granite. All right, so how about a little more detail about the interior of the Earth? The inner core is a solid ball of iron and nickel. Yes, you need to know all about the interior of the Earth for your third exam. The outer core is liquid metal. Liquid iron and nickel with a little bit of silica and oxygen. Okay, extra credit question here. How do we know the outer core is liquid? Well, it's going to have to do with something we're going to refer to as the S-wave shadow zone. So seismic waves from large earthquakes are going to travel through the subsurface. Well, seismic waves from all earthquakes are going to travel through the subsurface, and then those waves will propagate along the surface. But these larger earthquakes, you can actually detect the seismic waves on the other side of the planet. People are not going to feel that earthquake on the other side of the planet, but the seismometers will detect the waves. And this tells us a little something about the interior of the Earth. All right, so a brief introduction here to some earthquake waves that we'll get into more detail regarding these after the third exam. P waves are waves that leave the focus of the earthquake, travel outwards in all 360 degrees, and they're going to travel through both solids and liquids. They can bend or refract as they pass through liquids, but at least they'll still travel through the liquids. The S waves, however, are only going to travel through solids. Why is that? Because S waves travel in a shear motion. We think of them as shear waves, and liquids do not have shear strength. Now later in the semester, if there's time, we'll bring the Slinky to class and we will try to demonstrate how the P waves and S waves travel. So this gives us something called the S-wave shadow zone. So on the opposite side of the Earth from a large earthquake, you will pick up P waves but no S waves. Sorry, I didn't mean to hit advance. That's okay. We don't have to be able to drill down into the interior of the Earth to know what it's made of, because the seismic waves tell us everything we need to know. Okay, so the mantle, I'm going to want you to know how it behaves. Third bullet there. It behaves in a rocky fashion. We refer to it as the rocky mantle. But it does actually flow very slowly with time. So there's convective heat flow with time, but it's not molten. It is rocky. And what is it made of? Olivine. You can skip this. Okay, the asthenosphere is the upper part of the mantle. I'm going to want you to know how it behaves. It behaves in a plastic manner. What does that mean? It means that it's not molten, it's not magma, but it is going to flow and deform and move with time. Okay, so the asthenosphere has its own name because it's different from the rest of the mantle. And our lithospheric plates are going to behave in a rigid fashion, and they will slowly move across the plastically behaving asthenosphere. By the way, you're going to have a section on your exam with the interior of the Earth, and you're going to have to match the layers up to where they belong, and you're going to have to be able to answer questions regarding what are they made of or how do they behave. This is a neat little drawing here showing the asthenosphere, upper mantle, behaving as a plastic, and then you have the plate on top. The plate consists of crust and lithospheric mantle. The moho is your boundary there. You're going to notice here that the plate is thicker in a continental setting than in an oceanic setting, and that's primarily because the continental crust is thicker than the oceanic crust. Here's just another image of planet Earth, and again, over on the left, they have kind of a blown up version of what you find towards the top, the asthenosphere and then the plates, and our transition from continental crust granite to oceanic crust basalt. Okay, so the lithospheric plates, sometimes just called plates or just called lithosphere, again, they are comprised of two parts. The crust is on the top and the lithospheric mantle portion is on the bottom. Together, these things are going to behave in a rigid manner. Now, again, there's a funny name for that transition from crust to lithospheric mantle. It's called the moho, and we discovered the moho because of seismic waves. And we discovered that the seismic waves speed up at a certain depth pretty much everywhere on the planet, a similar depth, and we knew that that meant a change in density. In other words, the crustal portion of the plate is less dense than the lithospheric mantle portion of the plate. Okay, so here we're just looking at a very generalized image of some of the larger plates. Okay, and here's our moho. You do need to know what the moho is. Okay, so again, it's the crust lithospheric mantle boundary, and I'm going to want you to know where it's located. And it'll be part of that matching where you're going to match up the different layers of Earth. Here's just another image of the asthenosphere and then the plates above. Okay, I'm going to want you to know the thicknesses of continental plate versus oceanic plate. I'm also going to want you to know the thicknesses of continental crust versus oceanic crust. So here we're talking about continental lithosphere, as in the plates in a continental setting. What is your average thickness? That average thickness is 150 kilometers. And granite is making up our continental crust, and it is less dense than the oceanic crust. So even though a continental plate is thicker than an oceanic plate, that continental plate is still going to be less dense than an oceanic plate. So how about the thickness of oceanic lithosphere or oceanic plates? Average thickness only 100 kilometers, so not quite as thick. Okay, and the oceanic plates, of course, are going to have oceanic crust on top, which is basalt. So even though the oceanic plate is less thick than the continental plate, that oceanic plate will still be more dense than the continental plate. Continental crust. Well, you need to know that second bullet there. Oh, you need the third bullet as well. Really, you need to know all this, but we've mentioned some of this already. So continental crust is mostly granite. Okay, to be fair, you got metamorphosed granite at depth, and you have sedimentary rocks and sediments covering the top, but generally the dominant rock type there is granite in the continental crust. Average thickness of continental crust, just the top part of the plate, about 40 kilometers. I might ask you to know, or to be able to tell me, where do we find the thickest continental crust anywhere on the planet? And the answer is in the Himalayas, and it's 70 kilometers thick there. And does that surprise anybody? What do we know about the Himalayas? Aren't they the tallest mountains on the planet? Yes, they are. Mount Everest is there, and K2. So it kind of makes sense that that's where we find our thickest continental crust. How about oceanic crust? Well, as we mentioned before, it's made of basalt. The average thickness of the oceanic crust is really thin. It's only 7 to 10 kilometers. That's why an oceanic plate is not as thick as a continental plate. You can pause here if you want to and read a little bit more detail about our layers. Okay, now we're going to switch gears and we're going to discuss Alfred Wegener. We might think of him as the father of continental drift. We cover this in one of our video lessons, by the way. Okay, so Alfred Wegener, and that is misspelled there. That should be W-E-G-E-N-E-R. Alfred Wegener was a German meteorologist, and he was able to travel to many different continents, including Antarctica. He went to Antarctica at least a couple times, but he also just did a lot of good old-fashioned library research. So he's credited with first writing up the hypothesis of continental drift back in 1915. So he proposed that the continents fit together like a jigsaw puzzle, and more so if you fit them at the edge of the continental shelves instead of where the water is today. And he had a name for that supercontinent. Does anybody know what that was called? We call it Pangaea. So there were different lines of evidence that Wegener had for the existence of Pangaea. And we're going to list those on some upcoming slides, but one of the big ones was fit of the continents. So here you're seeing that South America and Africa, and here we're fitting them at the edge of the continental shelf. They match up perfectly. All right, so you're going to need to know the name of our most recent supercontinent is called Pangaea. That's also a typo. There should be an A in front of the E. Pangaea. That's what Wegener named the most recent supercontinent. So you would think that all the other scientists would be really on board with this new idea because Wegener had a lot of evidence, which we're going to get to, but actually they were not okay with it. And they actually ridiculed him for this notion of continental drift. And the big reason is that they wanted to know how it happened. Continents are very big and massive, and what kind of forces would be necessary to move continents. And he really cannot explain how this happened. It was not his fault. We did not have the technology yet to be able to figure this out. Anyway, why, exam question here, why did the scientific community at the time not buy into Wegener's theory of continental drift? And the answer is he could not provide a mechanism for continental drift. So here we're looking at, over on the left, you see Pangaea there, and you see all the continents together with their present names. Over on the right, you see Pangaea in its heyday, 225 million years ago. That's in the top left. Top right, we started to break apart Pangaea 200 million years ago. We basically separate the northern continents from the southern continents first. We're going to have special names for those. The northern continents are going to be called Laurasia, and the southern continents are going to be called Gondwana. In the Jurassic, we start to form a little bit of the North Atlantic Basin in the Cretaceous. Into the Cretaceous here, 65 million years ago, about to get hit with a meteorite that will help to take out the dinosaurs. You see there that the South Atlantic is getting larger, and the North Atlantic is starting to get larger. And then you see the continents in their present day configuration, what we are used to. Rodinia, or Rodinia, the British like to call it Rodinia. This is in one of your video lessons. This is the name of the supercontinent before Pangaea. So that is also an exam question. I'm going to want you to know the name of the supercontinent before Pangaea. We call it Rodinia. Anyway, there's an image of Rodinia to the left. And what you might notice, and of course that image is after Rodinia starts to break apart, you might notice that there doesn't seem to be as much land there as what we're used to now. And the answer there is that we just didn't have quite as much land at that time. It hadn't been created due to tectonic processes. So Rodinia was formed by about 1.1 billion years ago. If you would like to pause on the slide and read through this, you can do that. It's a really interesting slide here, talking about the breakup of Pangaea. Okay, so a little bit more about Rodinia. So formed by 1.1 million years ago, and it slowly rifted apart between about 750 and 550 million years ago. So Uwharrie National Forest is here in North Carolina, and it's just to the northwest a little bit, kind of like between Pembroke and Asheville, where the zoo is at Asheville. Anyway, it's free to get in. I recommend going there. I'm pretty sure that our parks and things are open again. I know a lot of things were shut down at the beginning of lockdown. Anyway, I recommend going to Uwharrie National Forest. It's really cool. And there's this topographic high referred to as Morrow Mountain, which isn't much of a mountain, but it is just kind of a hill. Anyway, we're pretty sure that that is the remnants of a once much larger mountain chain built when Rodinia was being assembled. Okay, Laurasia and Gondwana. I believe these are extra credit questions here. Laurasia is the name we give to the northern continents clustered together, and Gondwana is the name we give to the southern continents clustered together. If you take Earth history, you'll learn that there's a little more complicated history there to these two supercontinents. So these are basically smaller supercontinents that came together to form Pangaea and then split apart to form the globe as we know it today. Okay, so what was Wegener's evidence for continental drift? Fit of the continents, matching mountain ranges, say between South America and Africa, North America and Western Europe. How do you match up mountain ranges? Well, you have to go there and take samples and study them. Matching rock types, matching ages. Also, there were fossils of many land-dwelling organisms that could not swim across oceans. And these organisms, such as Glossopteris, Lystrosaurus, Synagnathus, and Mesosaurus, were found on, in particular, most of the continents that made up Gondwana. Okay, more evidence for continental drift. We found matching glacial deposits from past glaciers, matching coal swamps, matching salt deposits, matching dune deposits, matching reef deposits. Wegener's evidence is in one of our video lessons. Here we are just showing that the Appalachian Mountains in North America match up very well to mountains in Africa. Greenland and Nova Scotia matching up to mountains in Great Britain and Scandinavia. And then over on the right, that is, of course, a satellite image of the Appalachian Mountains. And you see the Chesapeake Bay in there just to kind of give you an idea of where you're looking at. Here's just another version of what we just looked at, how you can match up the Caledonian Mountains in Scandinavia, say, to the Appalachian Mountains in North America. So these mountains form together as one big mountain chain, and they are now separated by the Atlantic Ocean. One more thing that seem to match up from different continents, continental shields. This is in the list that I put on the board in one of those video lessons. So here the Brazilian shield matches to the West African shield. And what are continental shields again? They're the oldest original parts of any continent. We find parts of the Zimbabwe-Congo shield on South America, for example. Okay, so what do we mean by evidence of past glaciers? We don't mean where do we find glaciers today. We mean where did we have glaciers before that we maybe don't anymore, but we know that they were there. Okay, so on the bottom left, that of course is looking at the bottom of Gondwana. And of course on the top left, that is what our continents look like today. So what I'm going to point out to you is, say, southern India, sea level, close to the equator. Do we find any glaciers there today? No, it's a warm climate. But do we find evidence of ancient glaciers from back when India was down there clustered with Antarctica? Yes. And what is that evidence? It's that image on the right, glacial striations. The glaciers not only can move and erode sediment of all sizes, but it's going to carve scratches into the bedrock that we refer to as glacial striations. So what we're looking at here, this might look like a road bed, like they're going to build a road or they took the blacktop and they're going to smooth this over and put new blacktop down. No, this is all natural. This is, where is this image taken? That's a good question. Possibly Africa, in a place that's warm today, and these are those glacial striations from glaciers when Gondwana and all of Pangaea were together. So here we're looking at a map just showing matching deposits from past glaciers and then matching coal swamps. This is not the best image, so we'll move on to a better one. This is a better image. From which textbook? I don't remember. There's a lot of images in here from textbooks you don't have. That's a good thing. Okay, so what you're looking at, okay, so this is, of course, an image of Pangaea. You're kind of starting to break apart here. So let's look at the legend down at the bottom. The thing that looks like a palm tree, that's showing you coal swamps. So notice that the Appalachian Mountains, which today are, well, they're not swamps, they're mountains and highlands, but back then when the coal was forming, that part of North America was down at the equator, so no wonder you had all these coal-forming swamps. But we see matching coal from the Appalachian Mountains over into, say, Western Europe and Asia. What looks like a brown wave down there is desert sand, and we're not talking about matching modern deserts, but matching ancient deserts, looking at those large cross-bedded sandstones. The thing that looks kind of like a sunburst, those are matching ancient salt deposits. In the bottom middle, that looks kind of like a brick pattern. We always use a brick pattern to denote limestones. These are ancient reefs. And again, look over to the eastern part of North America, what is today the Appalachian Mountains. I have seen these coral reef limestones with my own eyes in the mountains of West Virginia. Okay, it's mountains now, it's highlands, it's not a shallow marine environment, but it was millions of years ago. This is a really good slide because it shows the different fossils. You do not have to remember the names of any of these fossils. Just know that matching fossils was one of the lines of evidence that Wegener had for continental drift. So in the bottom left, that's Syngnathus, and there in the baby aspirin orange, we find Syngnathus remains South America and Africa. Syngnathus was a land-dwelling animal, not swimming across an ocean. On the top there, that thing that looks like an alligator is a Mesosaurus. So, and it was kind of like similar to an alligator, but bigger, and it was a freshwater reptile. So again, it did not swim across the ocean. And we find it in Central South America, Central Africa. Then over there to the right in the darker orange, Lystrosaurus was another land-dwelling reptile. We find Lystrosaurus in Antarctica, India, and Africa. And then in the bottom right, even a plant, Glossopteris. Glossopteris certainly was not swimming across the oceans either, and we find Glossopteris remains on all of the continents that once made up Gondwana. Here's just a different version of that where the animals don't look quite so cartoonish. But again, the important thing here is that you can't explain the distribution of these fossils by saying that these animals swam across the Atlantic Ocean, because they were not marine swimming animals. Okay, so this is really cute here. We have some competing hypotheses. On the top left, rafting. Yeah, because you're going to get breeding populations to accidentally raft all the way across the Atlantic Ocean and not get swamped by a 3-foot wave. Top right, isthmus lynx. Well, we didn't have any such thing. So it is true that in the most recent ice age, the Wisconsin ice age, when sea level was 130 meters lower, it's true that there was a land bridge from what is today Russia to Alaska. And we did have migration of animals and humans, but we didn't have any such links linking up, say, South America and Africa or North America to Western Europe. Bottom left, island stepping stones. Nope, hardly any islands out there. Eventually you have to accept that continental drift is real. Of course, these days we refer to it as plate tectonics. Okay, Earth's magnetic field. I hope we have a little bit of time in class to talk about this, but I don't know that we will. So the image in the top right is basically what they're trying to show there, those things that look like little corkscrews. We have flow in the outer core, and that gives us our protective electromagnetic field. We'll talk a little bit more about that on an upcoming slide. Image on the left is showing magnetic field lines, and we always kind of image it as Earth having a bar magnet at the center. Well, we don't, but the liquid outer core metal convection kind of acts like a bar magnet. So we can imagine the electromagnetic lines coming out of the Earth at the South Pole, enveloping the Earth, protecting it from solar wind, coming back in at the North Pole. Now that 11 degrees there is not the tilt of planet Earth. Planet Earth's tilt is 23.5 degrees. What that 11 degrees is showing is how much the geographic North Pole is off from the North Magnetic Pole. Okay, this is an image here on the right. That's a computer model showing the magnetic field lines of planet Earth. Again, why do we have a magnetic field? Because of convection in the liquid outer core. Why does it matter? Because it helps protect us from solar wind. If we did not have a magnetic field, we might have life here, but it would be primitive and we wouldn't have life as we know it now. It helps to make life possible here. Okay, so magnetic declination. We usually spend a couple minutes talking about this in class. Why? Because, well, it could save your life someday if you're hiking. Okay, so magnetic declination is not on your exam, but it is important enough to spend, 3 minutes on. This is basically just saying that Earth's magnetic pole is different from the geographic pole. All right, and there is this thing known as the line of zero declination, and in this drawing here from roughly about 2005, you see that the line of zero declination kind of comes down, not quite in the middle of the United States, but maybe sort of near, kind of cuts through the Mississippi River at some point. It just means that anywhere on that line, if you were going to go hiking and you bought a brand new compass, as long as you stay on that line, you can navigate using that compass and you're not going to get lost. But if you are to the east or to the west of that line, the magnetic declination is going to matter. In other words, your compass is not going to read true north. Okay, and the further away from the line you get, the worse it is. And there they're showing a line that comes down maybe north of the Chesapeake Bay, and there your declination is off by 14 degrees. So just know that if you're going to hike in unfamiliar territory, you need to have a compass, you need to have maps, you need to have them in paper or already downloaded, because you know you're not going to have a signal out there in the woods. And you need to consult the map and find your magnetic declination and adjust your compass before you start hiking. By the way, here we're looking at, on the left, that's a computer model of Earth's magnetic field. On the right, that is a computer model of what we think the field lines will look like during a reversal. And why do I show that? Because I'm pretty sure we are going through the next magnetic field reversal. And it's nothing to be afraid of. We'll briefly discuss it on an upcoming slide. We're going to skip this slide. Okay, so here's a little something that is in a video lesson. How do we go from continental drift to plate tectonics? Okay, so remember Wegener, nobody believed him because he didn't have a mechanism. Wasn't his fault. He tried to, come up with a mechanism, and it didn't sound plausible because it wasn't the truth, but he didn't know any better. He proposed the continents broke through oceanic crust like icebreakers, and that's not what happens. The plates move, and the plates usually have both continental and oceanic material on them. So there were a lot of discoveries made in the 20th century after 1915 that helped tie everything together to plate tectonics. So World War II and plate tectonics. These things actually have a lot to do with each other. We discussed this in a video lesson. So warfare at sea during World War II, we were fighting in the Atlantic and the Pacific, and of course, us, the good guys, the Allied powers, we needed to find the enemy submarines before they found us. So we used sonar to try to find enemy subs. It involves making a sound, which they call a ping, and it travels through salt water, and when it hits something solid like the ocean floor or a big blue whale or an enemy sub, it's going to reflect and come back to the sub. And then you count the number of seconds that it took for that sound to come back, and you know the speed of sound in salt water, and then you can figure out how far away from you that solid object is. So we were, of course, trying to win the war, and we were eventually successful, but we also accidentally mapped the ocean floor, and that was a good thing. We call that bathymetry, by the way, or bathymetric maps. Before World War II, we didn't know much of anything about the ocean floor. So this is an image of the North Atlantic Basin, and that thing in the middle that looks like an alligator's back, that is a portion of the Mid-Atlantic Ridge. So to be fair, before World War II ever happened, we had found a tiny portion of the Mid-Atlantic Ridge. So the British ship HMS Challenger between 1872 and 1876 conducted cable soundings where they let a cable go over the ship to the bottom, and then you make a mark of, at what point you hit bottom, and then you reel it back up, and you have to measure it. Very high tech. Anyway, we had found a tiny bit of the Mid-Atlantic Ridge back then, but we had no idea how long the Mid-Atlantic Ridge is, or that we have these in every ocean basin. Not until World War II. Okay, so here we're looking at a nice image of planet Earth and the mid-ocean ridges, but what we also have there across the bottom is kind of a cross-section drawing showing features of the ocean floor. Okay, so when we accidentally mapped the ocean floor, we found all kinds of neat things like mid-ocean ridges, abyssal plains, seamounts, and deep ocean trenches. And each of these things that we found was a piece of the puzzle in trying to figure out how plate tectonics works. Okay, so exam question here. You're going to need to know that during World War II, we accidentally mapped the ocean floor. I'm going to ask you to be able to tell me, what did we find? We found mid-ocean ridges, like the Mid-Atlantic Ridge. These are undersea volcanic mountain chains. Yes, they're volcanoes. They're pretty gentle. They produce brand new oceanic crust made of basalt. And there are some earthquakes there as well. We also found abyssal plains, which are these deep, flat, basically featureless parts of the ocean. And the abyssal plains tend to lie in between the mid-ocean ridges and the coastlines. We also found deep ocean trenches, and these deep trenches line most of the perimeter of the Pacific Ocean, and we do have them in some other places as well. So the Mariana Trench is very famous. You may have heard of it. It's the deepest part of any ocean trench on the planet, and the deepest part of the Mariana Trench is 7 miles deep. So you might think, wow, it would be impossible for humans to go there. So do you think we've ever sent, and I don't just mean a rover, but have we ever sent humans in submersibles to the bottom of the Mariana Trench and brought them back safe? What do you think? Well, we have. We've done it twice. Okay, so the first time was back in about 1960. And there's a neat story there. We'll try to make it quick. A Navy person and a scientist, they were in this round bathysphere thing that they built, and they took them to the Mariana Trench, and this thing they were in was tethered to a cable, and they put these guys in it, and they sent them all the way to the bottom of the Mariana Trench. On the way down, they heard a sound. They weren't quite sure what it was. They didn't turn the lights on until they hit the bottom. Then they discovered, see, they had a double glass hull in this round bathysphere that they were in, and each glass hull was only 2 inches thick, and the outer hull had cracked, and that was the sound they heard. So what the thing they were in was already compromised. As you can imagine, they did not stay long, but they were able to bring them back to the surface successfully. They lived through it. And then Oh, the guy, the movie producer that did Titanic, James Cameron. James Cameron did some fundraising, and they built a few years ago, maybe 5, 7 years ago, they built some new craft, and he went back to the Mariana Trench, and this time they took some samples. It was a Discovery Channel episode about this. Okay, what else did we find in World War II? We found seamounts, which are these underwater submarine volcanic mountains that are extinct. They no longer erupt, but they did erupt in the past or they wouldn't be there, and they probably rose above wave base to make islands in the past. We also found fracture zones. Fracture zones are basically these large cracks or strike slip faults that are perpendicular to the mid-ocean ridge axis and accommodate plate movement. Here's another image of what typical bathymetry of the ocean floor looks like. Now over on the right, now you're kind of getting like a bird's eye view of the top of the mid-ocean ridge axis. So the downdrop valley there in the middle, and that's typical because plates are moving apart, and then those fracture zones there are going to offset segments of the mid-ocean ridge. Okay, so just a little something else about these fracture zones. So this is a kind of a simplified map showing these fracture zones, but they are important. And what do they allow for? They allow for movement of plates, and especially when you have different rates of movement. So to give a quick example, the Pacific Plate, okay, so look kind of off, see where it says East Pacific Ridge? Also, that's called the East Pacific Rise. About where those words are, you have the Pacific Plate moving at as much as 16 centimeters per year. But at the San Andreas Fault in California, it's only moving at about 5 to 6 centimeters per year. And then over in the Hawaiian Islands, it's moving at maybe 9 to 10 centimeters per year. So the same plate is moving at different rates of speed at different parts of the plates. And these fracture zones kind of allow for that to occur. Okay, other findings during the 20th century. This is also in a video lesson. So with the help of fancy oceanographic ships, high heat flow was discovered at the mid-ocean ridge, meaning that you get a heat signature there in the water column whenever your boat is going across the mid-ocean ridge. So Harry Hess, you do not need to know his name, but he's a famous geologist. He figured out, what's causing a heat signature here. It's got to be magma. There must be magma rising up into the crust there at the mid-ocean ridge. And it must be then, so it's hot, it's giving us a heat signature, and then it cools and solidifies and forms new basalt oceanic crust of the mid-ocean ridges. Guess what? He was correct. Here's just a drawing of that heat signature over the mid-ocean ridge. Okay, so other things we discovered in the 1900s. If you plot active volcanoes and earthquake epicenters on a world map, it's not going to be random. It's going to have a pattern. So this is probably a better image of that. Volcanoes and earthquake epicenters worldwide. All right, so in the red triangles, those are volcanoes that are above wave base, subaerial volcanoes. There's also a bunch of submarine volcanoes here that they're not plotting, but we know that they are there at all the mid-ocean ridges. In the blue circles, you see earthquake epicenters. So you've got active volcanoes and earthquakes plotted on a world map. And it's not random. Okay, it's not like, buckshot on a target at the shooting range. This is, it has a pattern. So in those yellow lines there, basically what they've done is connect the dots. Now, if we have time in class, I'm hoping to show this image, and I'm going to ask everybody, what do those lines mean? Okay, and usually I've got one or two people that will give me an answer. Maybe other ones have come up with an answer and are just too shy to give me their answer. But those yellow lines are plate boundaries. So connecting these dots gives you the outlines of the individual plates, the large ones anyway. What else was cool that happened in the 20th century that helped us figure out how our planet works in plate tectonics? Well, radioactivity first discovered in 1896, but we perfected being able to figure out the ratio of parent to daughter material. and get a radiometric age date of rocks not only in the continental setting, but oceanic rocks that were drilled with those big oceanographic vessels. And of course, this allowed us to compare the ages of rocks, that the oldest continental rocks, 3.96 billion, and that the oldest oceanic rocks in an ocean basin are at most 180 million. All right, so on the right, this is an image of one of those fancy oceanographic vessels. So that thing in the middle that's really tall, that's a drill rig, and that's one of the points of having a boat like this, or buying access to this boat, is that you can drill down into the oceanic crust. And then that flat thing over on the right is a helicopter landing pad. On the left there, we're just looking at a mid-ocean ridge and the oceanic crust on either side. Remember that the plates move apart here, and then you're looking at the thickness of sediments, and that the thickness of sediments is going to get thicker as you move away from the oceanic ridge. Just telling you that that rock, as you move away from the ridge on either side, is going to be older. This is another image of that same ship from above, or a similar ship. You got your drill rig there, you got your helicopter pad, and then over on the right they're showing how, if the seas are calm and it's a good, few days to work on this, that you're going to drill down into not only the sediment but the oceanic crust below. This is one of those fancy ships. It's called the Joyde's Resolution. It can hold a lot of scientists and crew, and what happens is that university professors and other researchers apply for grant money with the National Science Foundation and are able to rent time on these boats and go conduct research. I have to admit, I'd love to be a part of that. What else do we find in the 20th century? This is one of my favorite things here. Marine magnetic anomalies, also referred to as seafloor stripes. Okay, so we discovered if you take a research vessel across an ocean basin and you happen to bring a magnetometer that you tow behind the boat, you're going to find, or it's going to appear that you have strong and weak signals for the magnetic field. And they're going to alternate. You got a strong signal, you got a weak signal, strong and weak. So what did that mean? Did that mean that Earth's magnetic field was not that strong? Or did it mean something else? So this is an image I hope we have time for in class. So you see the seafloor there with the dark basalt rock. You see your ship, and you're bringing your magnetometer there. And of course, in World War II, we're using the magnetometer to try to find what they refer to as depth charges, or these basically bombs that the enemy would put in the water, hoping that we would run into it, and vice versa. Anyway, so what we discovered, look at the image across the top, there's a printout of it, that you'll have some length of time that you're moving along, and Earth's magnetic field, appears to be very strong. And then it'll be weak, and it'll be strong again, and then weak again. So what's going on here? Well, the magnetometer are not only reading Earth's present magnetic field, but they're also reading the signature of magnetite crystals in the basalt on the ocean floor. Magnetite is a mineral found in basalt, and it is naturally magnetic. Okay, so how does this work? Paleomagnetism. In the drawing on the top there, imagine that that's part of the mid-Atlantic ridge. It's underwater. And as you have new melt forming, while it's still molten, your magnetite crystals grow out of the melt, and they're just pointing in whatever direction. But as that material cools and you drop below a certain temperature, then the magnetite crystals in the basalt will align themselves with whatever Earth's magnetic field is doing at the time. So that arrow pointing down means normal polarity. Normal polarity meaning the polarity that we have today. Okay, so what all does this mean? Well, it means that Earth's magnetic poles flip from time to time. It's been doing this as long as we have had an outer core and a magnetic field. Okay, this is normal and natural. It's nothing to be scared of. There in the top image labeled A, that is normal polarity, what we're used to today. Arrow pointing down is normal, and then down at the bottom when the arrow points up, that is reversed polarity. So earlier in this presentation, I showed you guys a picture of a computer model of what the lines will look like when we go through the next flip. And the lines don't completely go away, they're still there, they just look weird. Anyway, I think we're in the early stages of going through the next flip, but we don't need to be afraid of it. We're still going to have a protective magnetic field. It might mess with navigation a little bit and communication here and there. Okay, so this really is the best image of all of these. So what do these seafloor stripes or marine magnetic anomalies mean? Okay, here's what it means. So let's look at the image across the top. Let's go to the middle there where it says mid-ocean ridge. That's part of the mid-Atlantic ridge. Notice that the arrows on either side of the ridge axis are pointing down. Okay, what that means is that in that part of the ocean, we get a strong signal. Does that mean that the electromagnetic field is extra strong and protecting us more here? No, it doesn't. It just means that electromagnetic field is doing what it's been doing for 700,000 years, and the magnetite beneath our boat is aligning with that, so it looks like a strong magnetic field. But on either side of that, the arrow is pointing in the opposite direction. So that tells you that you had reverse polarity when that crust on either side there was formed. And that manifests as looking like a weak signal. Does it mean that you don't really have magnetic field there? No, it does not mean that. It just means that the magnetite crystals beneath your boat there are pointing in the opposite direction. So these are the seafloor stripes, so the marine magnetic anomalies. So you really need to write down what's there at the bottom. What's important about this? Seafloor stripes helped prove seafloor spreading. Or they proved what Harry Hess had put forth, that it must be that the plates are moving apart and that we therefore have melt and that new basalt oceanic crust is forming there at the mid-ocean ridge. So what we're going to do in class together, hopefully, and we'll do it now, is we're going to look at either side of this image. Okay, so we're going to look at the far right and the far left where it's light gray and the arrow is pointing up or opposite. All right, so in both of those cases, the crust has reverse polarity. And if we were to take one of those oceanographic vessels and drill into the seafloor and take samples, we would find that on either end of that, let's say our age date is 50 million years. Okay, so what does that mean? It means that 50 million years ago, those two parts of the seafloor that are now spread apart by many kilometers, they were together. They were together where? At the center where the mid-ocean ridge is. Okay, so this is how seafloor stripes help prove seafloor spreading. Hopefully we'll take time for this in class. This is another example. It's not just in the Atlantic Ocean. This is a really small, couple of small ridges called the Juan de Fuca Ridge and the Gorda Ridge, and here we see those seafloor stripes as well. So where the red line is, and you have a darker color there, that's normal polarity, and then on either side from there, where you have a lighter color, that's reverse polarity. And these seafloor stripes are mirror images of each other on either side of the mid-ocean ridge. Again, this is proving that we have seafloor spreading occurring here. All right, so bottom line, it turns out that Earth's magnetic field has not always had normal polarity that we find today. It has reversed many times in the geologic history and will continue to do so. So Vine and Matthews, you don't need to know their name, but they are important, well-known geologists as well. They were working on these magnetic stripes, and then they kind of put that together with what Harry Hess had said. And basically, working together, they all showed that, yep, seafloor spreading happens at the mid-ocean ridges. Okay, so the magnetic reversals, you don't need to write this down, but just know, just for your own knowledge, we have had normal polarity for the last 700,000 years. We think it takes about 1,000 years for a reversal to occur. I personally think there is evidence in the South Atlantic Basin that we might be in the early stages of a reversal. Why? Because there's something referred to as the South Atlantic anomaly There are places in the South Atlantic basin where compasses are reading completely opposite. So I think we're in the early stages of a reversal, but don't be afraid of that. We will be okay. Okay, so you want to write down this middle bullet here. I mean, you should be taking notes as you're watching this, especially for anything that we didn't get to cover in class together. So remember that Wegener, they didn't want to believe his hypothesis continental drift because he didn't have a missing mechanism. And then by the later 60s, we had basically put all the pieces of the puzzle together, including kind of figuring out the mechanism. For now, this is what we're going to say, that the mechanism for continental drift, or plate tectonics, is related to convection in the rocky mantle and plastic asthenosphere. We will see on the last handful of slides that the plates actually kind of are going to help drive themselves around. We're going to call those driving forces on the plates, and we'll do that at the end of this unit. So it took decades and the work of many scientists working on different pieces of the puzzle, not necessarily knowing they were working on the puzzle, to finally put all that together and figure out how planet Earth works and synthesize the theory of plate tectonics. Okay, so if you look at only the larger plates, Earth's surface is broken up into roughly 16 large lithospheric plates. If you count all the small plates and the microplates, there's dozens of them. But, you know, there's 16 major plates. And, of course, these plates are going to act in a rigid, rocky manner, slowly moving across the plastically behaving asthenosphere. So here's an image showing the major plates. Let's find North America. There it is in yellow. Something that I mentioned in one of our video lessons, find the East Coast. Okay, that's where we live, right? We're real close to the coast. The East Coast is not on a plate boundary. Therefore, we're going to refer to it as a passive margin. Our nearest plate boundary to the east is the Mid-Atlantic Ridge. The West Coast, however, is on a couple of different plate boundaries, so we're going to refer to that as an active margin. Our nearest plate boundaries to the west would be the San Andreas Fault and the Cascadia subduction zone. Here we are looking at a map of the ocean floor, and they're just showing us the rate at which we have separation at the mid-ocean ridges. So I'm going to call your attention kind of near where it says Nazca Plate and Cocos Plate. That part of the East Pacific Rise is some of the fastest plate movement on the planet. You've got 17 to 18 centimeters per year of separation. Now look in the Atlantic. The Atlantic is much slower, anywhere from 4.1 to as low as 1.8 centimeters per year of spreading. Plate boundaries. So plate boundaries basically has its own video lesson, and it's an older one that I created a few years ago when I started teaching this online. So what is a plate boundary? It is the intersection of 2 or 3 plates. Some coastlines lie on plate boundaries, some do not. As we mentioned on a previous slide, the East Coast is not a plate boundary, so we call it a passive margin. So we don't tend to have active volcanoes here, and we don't have near as much earthquake activity as the West Coast. And again, a coastline that lies on a plate boundary is referred to as an active margin. And the West Coast is an active margin. It lies on 2 plate boundaries, the San Andreas Fault and the Cascadia subduction zone. Okay, so the plate boundaries. We will explain these as we go through the PowerPoint, but I expect you guys to watch the video lesson on this as well, and that's where you get your notes on the board, which really help in explaining these things. So there are 3 basic types of plate boundaries: divergent, convergent, and transform. And the names basically tell you what the plate movement is like. In divergent boundaries, plates move apart. We're going to find those in a continental setting and an oceanic setting. In a convergent boundary, plates move together. We'll have 3 types of convergent boundaries. And then in transform boundaries, the plates will slide past each other, a lateral type of movement. We'll see that the San Andreas Fault is going to be one of the best examples of a transform boundary. So we're going to break these down into different subtypes. So divergent boundaries may occur in either oceanic plate setting or a continental plate setting. If they are in an oceanic setting, oceanic lithosphere, we refer to them as mid-ocean ridges. We can also refer to them as spreading centers. So the Mid-Atlantic Ridge is a perfect example of that. If your divergent boundary is in a continental setting, then they are known as rift zones, and the East African Rift is the best example of that. Here we're looking at a very simplified drawing of a divergent plate boundary in an oceanic plate setting. Say, in this case, the Mid-Atlantic Ridge. Plates moving apart on either side. You get some decompression melting there of the asthenosphere, upper mantle, fueling the melt that gives you basalt that forms brand new oceanic crust at the mid-ocean ridge. This is a neat thing here. The Gulf of California has not always been there. The Baja Peninsula used to be part of mainland Mexico. So what's going on here? What's going on here is that the East Pacific Rise, which is a spreading center, cut through Mexico and took that land that is now the Baja Peninsula and separated it away from the mainland, creating the Gulf of California. Where it hits land, it then transitions into the San Andreas Fault. Okay, here's an image of melt occurring in a continental divergent boundary. In this case, the East African Rift, which is the only active continental rift on the planet. So even though it's a continent and the plate is thick and the crust is thick, you can have stretching and slowly pull this continent apart, and you're going to thin the crust, and you're going to have partial melt of the asthenosphere, fueling volcanoes such as Mount Kilimanjaro in the East African Rift. Okay, so more on divergent boundaries. Continental rifts may or may not complete rifting. The East African Rift is an example of an active rift zone. And I'm going to ask you to know that. You're going to need an example for each of these plate boundaries. I'm also going to ask you to give me an example of a failed rift. So in Missouri, near a city called New Madrid, is something we refer to as the Reelfoot Rift. And it is a failed rift, as in a rift that did not complete. As in millions of years ago, North America attempted to split apart here and was not able to. But it left behind big faults that do occasionally cause large earthquakes. We'll get into earthquakes after the third exam. Here's a nice drawing, well, especially over there on the left. Well, the map, I guess, over on the left. That shows the East African Rift. This is a place where you have a continent actually splitting into two pieces. And then you have these linear lakes, because water is going to fill up these downdropped areas. And Mount Kilimanjaro and Urta Ale are well-known active volcanoes that are occurring in the rift. Here's another map showing the East African Rift. The red is deceiving. It's not saying we got a bunch of lava spilling out there. That's just showing our downdropped areas that tend to fill up with water. Oh, Mount Kenya. I always forget about Mount Kenya. It's another active volcano in the East African Rift. Okay, so kind of neat here is you also have the Red Sea, which is kind of to the northwest of the East African Rift, and then you have the Gulf of Aden, is that body of water to the right. And the Red Sea is neat. This is also a spreading center. There's a little mid-ocean ridge there. And we have evidence of that from the volcanism that's occurring here. But what we don't see in the Atlantic is you don't see the mid-Atlantic ridge sticking up above wave base. But you do see that here. Okay, and what makes the difference? I asked this question in class and hardly anybody kind of, gets an answer. But the Red Sea has much more shallow water. Therefore, you do actually have that little mid-ocean ridge exposed. You got some of the islands sticking up above wave base. Here's another drawing of the East African Rift Valley. Here's a nice image of Mount Kilimanjaro, and then with a giraffe in the foreground. Does the giraffe make very good scale? Not really, but that's okay. Okay, more on divergent boundaries. So our oceanic divergent boundaries lead to mid-ocean ridges like the Mid-Atlantic Ridge. Continental divergent boundaries will give you crustal thinning, and they may form a new ocean basin if the rift completes. Is it possible that the East African Rift will complete and that we'll have an ocean basin in there someday? That is definitely possible. Continental divergent boundaries that fail will leave behind faults that will accommodate plate movement in the future and lead to potentially large earthquakes, like in the case of New Madrid, Missouri. Here's a nice step-by-step drawing, say showing us the breakup of Pangea. At time 1, you've got Pangea. At time 2, you start to stretch. You start to pull things apart. You're going to form these little downdraft valleys and these rotated blocks, and the crust is going to get thinner. At time 3, you keep on stretching, and the crust gets thin enough that you have melt, and you start to have volcanoes. In the case of time 4, you continue to pull these things apart, and you have more melt, and eventually your melt is going to change from felsic to mafic, and now you start to form a bunch of basalt in this downdrop area. You're forming a brand new, very tiny ocean basin, and then in time 5, the ocean basin is getting larger. This is a different way to show the same thing, but what I like about this image here is notice that big red thing beneath where the rifting starts. What they're trying to show here is a hot spot, a mantle plume in a continental setting. That's one means by which you can start to form a continental rift and tear a continent apart. And in this case, again, we'll say, hey, this goes back to breakup of Pangea and forming the Atlantic Ocean as we know it today. All right, exam question here. What happens to oceanic crust as it moves away from the mid-ocean ridge? 3 basic things. You really just need to write down what's underlined. As you form brand new oceanic basalt crust at a mid-ocean ridge, and then on either side it moves away from each other, what happens is it becomes older, colder, and more dense. So it just simply gets older as it moves away from the mid-ocean ridge. So it's also going to lose heat with time and get colder, and as it loses heat, it will get more dense. This will be important when we have 2 oceanic plates trying to occupy the same space at the same time. Okay, so what kind of geologic phenomenon will you get? At oceanic divergent boundaries, mid-ocean ridges, you're going to get volcanoes producing basalt and relatively shallow earthquakes that are not super strong, and you tend to not produce tsunamis here. At your continental divergent boundaries, you're going to thin the crust, you're going to produce earthquakes, then can be large earthquakes. Eventually, you'll get active volcanoes if the rifting does not fail. Okay, so a potential extra credit question here. The Basin and Range Province. This is occurring in the western states. I'll show you a map of where it happens on the next slide. And what we have is just simply stretching. This is not a rift zone. It may never become a rift zone, or it might. Right now, it's just crustal thinning and stretching. It's called the Basin and Range Province. So the Basin and Range Province is quite extensive. You see a map here. It's western Montana, all of Idaho, eastern Washington, eastern Oregon, eastern half of California, all of Nevada, half of Utah, and then it gets skinny and it kind of snakes down into Arizona, New Mexico, branches off to go to Texas, and then up into Colorado, where it has its own separate name, the Rio Grande Rift. This is just saying that this part of the United States is stretching. It's being pulled apart. Okay, we're now to our second major type of plate boundary, convergent plate boundaries, where you have plates coming together. And because we have 2 types of plates, oceanic and continental, and you bring those together, you can make 3 different combinations. So 3 types of convergent plate boundaries. You got ocean to continent, you got continent to continent, and you got ocean to ocean. Are you going to need to know this for your exam? Absolutely. You're going to need to know an example for each of these as well. And again, this is still in a larger unit called plate boundaries, and you have a, I think, 20 to 30 minute video lesson on that. Okay, so we're going to begin with ocean to continent. So when you have an oceanic plate smacking into a continental plate, this forms a subduction zone. What this means is that oceanic plate and crust is more dense than the continental plate and crust. Therefore, the oceanic plate is going to sink beneath the continental plate. I know that sounds crazy. How can that happen? Oh, it happens. We're going to see a drawing. Here you go. Here's a great drawing of the Juan de Fuca oceanic plate sinking beneath the North American continental plate. So what's going to happen here? Well, lots of things. This is not an easy process, so you can form some very large, devastating earthquakes here. The largest earthquakes that we tend to see, your 9.0 to 9.5 tend to be at our subduction zones. You're going to get partial melt of that subducting slab due to dewatering. That's going to fuel active volcanoes on the overriding plate, like Mount Hood, Mount Adams, Mount Rainier, Mount St. Helens, within the Cascades continental volcanic arc. And you're also going to thicken the crust. So you're forming mountains in general, and some of those peaks will be active volcanoes. And there at the top is a nice picture of Mount Hood, Oregon. Look how pointy it looks. That's a stratovolcano, the scary kind. We'll do volcanoes in our next unit after plate tectonics. Okay, exam question here. Is it possible for some subducting oceanic plates to make it down to the core mantle boundary? And the answer is yes. How do we see that? Seismic tomography. Speaking of seismic tomography, this is a real image. Okay, this is in the Western Pacific, the Tonga Trench and the Tonga Island Arc. Those things that look like birthday hats are active volcanoes. So basically, we're just studying seismic waves. Seismic waves speed up when they hit something of a greater density, like a cold, dense, sinking oceanic plate, and they slow down when they hit something of a lower density, like the hot asthenosphere mantle. So in the green there, you see your sinking plate. So in this case, it's actually an oceanic plate sinking beneath another oceanic plate, making a big trench, forming active volcanoes that are islands, and causing a lot of earthquakes. How do we know all this? Seismic tomography, mapping out the changes in speed of our seismic waves. Another image here is seismic tomography. So I might ask you on the exam, and this will be on your study guide. What is the name of the technology that allows us to image subducting oceanic slabs? And that answer is seismic tomography. So the image on the top is the Cocos plate subducting beneath the Caribbean plate. And in blue, that's your cold sinking plate. And in red is your asthenosphere mantle around that. The image in the middle is where the Cocos plate sinks beneath the North American plate there in Central America, Mexico. And you see there that the angle of that subducting slab can change. And then in the bottom image, that is the Nazca plate, oceanic, sinking beneath the South American plate, continental. And you see that sinking plate sinking at a more steep angle. And in all these cases, you are going to thicken the crust, you're going to form mountains, you're going to have active volcanoes, and you're going to get big earthquakes. All right. Yes, this is a potential extra credit question on the third exam. What is the name? Okay, so what is the name of the plate that is subducting now beneath North America and the Pacific Northwest? And that answer is the Juan de Fuca plate. But your extra credit question here is, there is a plate that is beneath North America now and has subducted in front of the Juan de Fuca plate. We call that the ancient Farallon plate. And the Juan de Fuca plate, Gorda plate, and Cocos plates, and Nazca plate really are all remnants of this ancient Farallon plate. The Farallon plate was around, say, in the time of Pangaea. Okay, so what kind of geologic phenomenon do you have where you have an ocean to continent subduction zone? You get a deep ocean trench. If it's close to land, it may fill up with sediment and form an accretionary prism. So you get this chain of active volcanic mountains on the overriding plate. We refer to this as continental volcanic arc. Our best example is the Cascades Mountains in the Pacific Northwest. You get active volcanoes, you get strong earthquakes, you can get tsunamis. So this is a decent image. Here we're showing the Pacific Northwest, Northern California, Oregon, Washington. The Juan de Fuca oceanic plate sinking beneath the North America continental plate. You get some partial melt. You're going to thicken the crust and build mountains. You're going to have partial melt to fuel active volcanoes like Mount Shasta, Mount Rainier, Mount St. Helens. That picture on the left is Mount St. Helens back on May 18th, 1980. And then the map there at the top, you see the San Andreas Fault in green north of San Fran. It runs offshore and transitions in the Mendocino Fracture Zone. And then you have your subduction zone plate boundaries. The small Gorda plate and Juan de Fuca plates that are oceanic sinking beneath the North American plate. So the Pacific Northwest is a potentially dangerous place to live. There's a lot of geologic hazards. Here's another image showing really all the west coast. The San Andreas, well, you have the East Pacific Rise down there in the bottom right, and then the San Andreas Fault, and then the Cascadia subduction zone there. Here's an image of some volcanic peaks within the Cascade Mountains in the Pacific Northwest. So here is just another example, so it's not all about the Pacific Northwest. This is South America in the Andes Mountains, where you have the Nazca Plate subducting beneath the South American Plate. And same thing, you're going to thicken the crust, you're going to build mountains, you're going to have active volcanoes, such as a Somo volcano. There's a picture of it right there. Notice how pointy it is. This is absolutely a stratovolcano. Accretionary prism, we're going to skip it, it's not on your exam. Okay, so our second type of convergent plate boundary is called ocean to ocean. They're both oceanic plates. So who decides, who wins the battle? Well, the answer is that one of those plates will be older and therefore more dense than the other. So the more dense of the two will subduct. What are you going to get? Active volcanoes, of course, earthquakes, and potentially large tsunamis. So some examples here are, well, first of all, you're going to see something about this in our video lesson on plate boundaries. So when you have two oceanic plates coming together, the more dense of the two will sink. And you're going to have a chain of active volcanoes on the overrunning plate. And in this case, in an oceanic setting, we're going to refer to it as a volcanic island arc. What's a good example of that? The Aleutian Islands in Alaska. You're also going to get deep ocean trenches like the Mariana Trench. And the Mariana Trench, by the way, what we've already discussed, at its deepest, it's 7 miles deep, but it's 1,500 miles long, and is very productive at destroying oceanic crust. I guess we could say it's very destructive. Every 50 million years, it destroys an area of Pacific crust equal to the area of the United States. Crazy. And there's a correlation between age of oceanic crust and depth of trench. If the crust is really, really old, that trench is going to be very deep. And the particular place where they have sent people twice, where it's 7 miles deep, is called Challenger Deep. And here the slab is basically torn like a flap and descends nearly vertically. So here's a great example of ocean-to-ocean convergence. Here you have the Pacific Plate sinking beneath, well, there's a boundary there you can't see, but you've got the North American Plate on the right and then the Eurasian Plate on the left. But there where you have the chain of islands, you have oceanic plate sinking beneath oceanic plate. Volcanic island arc, called arc because they kind of curve. You got a whole lot, many bunches of active volcanoes here, like the Cleveland volcano, for example. I think that's a picture of the Cleveland volcano there. Here is a map of another famous location where you have ocean-to-ocean subduction. Okay, and this is a famous place. This is Indonesia. And right there where you have that purple star, that was the epicenter of the very bad large earthquake. I believe it was a 9.1 earthquake and devastating tsunami that happened there in Indonesia back in 2004 on the day after Christmas. Okay, finally, a drawing of an ocean-to-ocean subduction zone. Although you can see a drawing when you watch the video lesson on plate boundaries. So, and ignore the drawing on the top. It's got more information than we need. The one on the bottom is fine. Two oceanic plates, both relatively the same thickness and same density, but the one on the right is older, therefore it's a little more dense, so it will sink. You're going to have a deep ocean trench. You're going to have melt of that subducting slab due to dewatering, and you're going to fuel active volcanoes on the overrunning plate, referred to as volcanic island arcs. Okay, so again, the Aleutian Islands are a great example of a volcanic island arc, and there's a picture of one of those volcanoes erupting. They're very active, by the way. It's kind of common to have to, divert air travel, say from Eurasia over to North America because of eruptions here in the Aleutian Islands. Here's another drawing of your ocean-to-ocean subduction zone and forming those islands, volcanic islands, like the Cleveland volcano there. Okay, our third type of convergent boundary is referred to as continent-to-continent collision. Okay, so in this case, it's two continents. There's no oceanic plate at all. It's two continental plates. So they're both thick. They're both basically equal in density because they're both granite. So you don't have any subduction. You don't have a plate sinking beneath the other one. What are you going to get here? You're going to get extreme mountain building. You're going to get extreme crustal thickening. You're going to get large destructive earthquakes. You're going to have landslides and avalanches. And you're going to thicken the crust and you're going to form folded mountains. So imagine taking like a long rug that might be in a hallway and then pushing it from one end and watching it fold into form. So you're going to get folded mountains. You're going to form all kinds of faults, dangerous faults. You're going to get very large earthquakes. You're going to form mountains that are really tall and thick like the Himalayas. Now, you're generally not going to have any active volcanoes here, but you will have lots and lots of regional metamorphism. So our best example of continent-to-continent collision is the Himalayas, India pushing into Eurasia. Now in parentheses there, you don't need to know for your exam, but it's interesting. Early on, as India left Pangaea 200 million years ago, remember it was way down there with Antarctica, and first began to collide with Eurasia 45 million years ago, there was some oceanic lithosphere in front that has subducted. But at this point, that oceanic lithosphere has been consumed, and it's now continent-to-continent collision. And these continental collisions are going to give us the tallest mountains on the planet and the thickest crust. 70-kilometer thick continental crust in the Himalayas. Tallest mountains as well, like Mount Everest and K2. Here's a nice drawing. Well, the top anyway. Look at the top two images, right and left. On the left, that's what it looked like when you had some oceanic material in front of the continental portion of India. So it began as an ocean-to-continent subduction zone. So you would have had active volcanoes millions of years ago. And then over there on the right, time 2b, that's what it looks like now. So we can imagine actually the oceanic portion of that plate detaching and sinking, being on its journey to the core mantle boundary. And now you've got basically two continents crashing into each other, making very thick crust, very tall mountains, and lots of regional metamorphism, but no active volcanoes. Here's another drawing of the same thing. So where are the Himalayas? Here they are on a political map. And Mount Everest is actually pointed out there, not too far from Kathmandu. And again, this is because of India crashing into Eurasia. So here's an image taken from the Himalayas. So they're up above the tree line. Notice where they're stepping, there's not much snow, but there's snow year-round on the taller peaks, and they're hiking in the daytime, and it's sunny, so they're wearing their short sleeves. And of course, they're bringing all their stuff with them because they're going to have to camp out there. So in this image here, I like to show this in class, although I don't think we'll have time. You see the steep mountain peaks here and all the snow, right? Now I want to call your attention over to the left. See where that tent is? Oh my God. So they're trying to summit one of these tall mountains, and it takes days, so you got to camp out. Okay, and so where are you going to put the tent? Well, it's better to have it, on that rock there. That's a really steep angle. On the snow, how far do you have to dig down to anchor it into a rock? And then, of course, whoever is in that tent, well, your weight is going to be constantly pulling on that tent. You get in that tent, you're just rolling down there to the bottom of it. I think this looks terrifying. And another different example of continent-to-continent collision would be the Alps. This is in Europe. The Alps formed as a microplate, which included Italy, collided with the Eurasian plate. The Appalachians would be another example of continent-to-continent collision in the past. So there were three different mountain building events between North America, Europe, and Northern Africa, forming the Appalachian Mountains. And if you've ever heard of Mount Etna, It's a very active, like erupting every year, very active and well-behaved volcano. And you kind of associate it with Italy, but just know this, it's not in the Alps. Okay, we don't have active volcanoes in the continent collision. Mount Etna is actually on the island of Sicily, so it's further south and it has a different kind of plate boundary going on. So where are the Alps located? Here they are. So they're kind of in between Italy and a bunch of different parts of Europe. So you got Australian Alps, you got Swiss Alps, you got Italian Alps, you got French Alps. I have to admit, I'd really like to go see the Alps someday. All right, finally, our third type of plate boundary is called a transform boundary. What happens here is that the plates are not diverging and they're not converging. They're going to slide past each other in a lateral sense. So what happens here? What do you form? Well, you're going to form the world's biggest strike-slip faults. So the best example is the San Andreas Fault in California, which is an 800-mile-long strike-slip fault. It is also a transform boundary. It's where the Pacific plate kind of moves sideways with respect to the North American plate. Other examples would be the North Anatolian Fault in Turkey, the Alpine Fault in New Zealand, and the Woodstock Fault in Charleston, South Carolina. So, in a transform boundary, you don't have any active volcanoes. Why? Because you don't have a subducting slab to cause melt, and you don't have plates moving away from each other to cause melt. So you're just not going to have any melt. And no, we don't have any hot spots on the San Andreas Fault. What are you going to get, however? Strong, shallow earthquakes that can be really, really deadly. Examples are the 1989 Loma Prieta quake near San Fran due to the San Andreas Fault system, and then the 1994 Northridge quake down in the Los Angeles area. That was a blind thrust fault and not the San Andreas Fault. We will learn more about these earthquakes after the third exam. So again, we're looking here, we've actually seen this image before, but we're looking at it again. In this case, you have the San Andreas Fault. So that's a transform boundary. So again, there's two completely different types of two completely different types of plate boundaries out there on the West Coast. And then here we have a nice map of the San Andreas Fault transform boundary, and you see that to the south of that you have the East Pacific Rise spreading center, and then to the north of that you have the Cascadia subduction zone. And then in the top right you see an image there of the San Andreas Fault trace out in the desert portion of California, out in the Carrizo Plain. Okay, so neat images here. Again, on the left, you've got an image of the San Andreas Fault out in the Carrizo Plain of California, and on the right, well, your San Andreas Fault runs kind of right to left in the middle of this image, and then notice you got this dry creek bed cutting across there, and that dry creek bed has been offset by movement on the San Andreas Fault. And here is a zoomed-in image of that. So this is Wallace Creek. Pallet Creek does the same thing, but this is Wallace Creek. So you got the North American plate up there to the top of the image and the Pacific plate there to the bottom of the image. The offset there is about 300 feet. Okay, so that's a lot of offset. In other words, the two parts of this creek are being carried far away from each other with time, with just, earthquakes throughout time. So, back in 2010, there was a very devastating earthquake in Haiti. And that was on one of these transform boundaries, strike-slip faults called the Enriquillo Fault. And you see the epicenter there, and that was near the Port-au-Prince, Haiti. That was a devastating earthquake. 10 years ago, my goodness. And guess what? They still haven't recovered. So the Caribbean is a potentially dangerous place to live when it comes to plate boundaries. So here, this is just trying to show, your three basic types of plate boundaries and where they might occur on our planet. Benioff-Wadati zone. You're going to need to know bullets 2 and 3. This will be on your study guide. I'll go ahead and print those soon. So if subducting slabs can make it to the core mantle boundary, that might beg a question. So do they continue to have earthquakes all the way down to the core mantle boundary, or is there some cutoff? In other words, what is the deepest depth at which we detect earthquakes? And the answer is there's a cutoff. At about 660 to 700 kilometers is the deepest depth that we detect earthquakes on a subducting slab. By the way, we have a name for this zone. It's called the Benioff-Wadati zone. Refers to earthquakes along a subducting oceanic slab. In other words, you get below that depth of 660 to 700 kilometers, and that slab no longer acts like a brittle solid. Here's a nice drawing of that Benioff-Wadati zone. Okay, mid-ocean ridge. You don't have to write any of this down. We briefly discussed this in a normal semester together. This is a zoomed in look at, say, the mid-Atlantic ridge, and you have your plates moving apart on either side. This allows for upwelling of the asthenosphere below. Okay, so the asthenosphere, remember, it's not molten, but it's a solid, but behaves as a plastic. And as you move as the plates move away from each other at the mid-ocean ridge, the asthenosphere is hot and buoyant, so it's going to rise up to fill that void. And then, of course, that allows for decompression melting, fueling these magma chambers that are going to give us these basically underwater, kind of like shield volcanoes, basaltic melt. So the mid-ocean ridges don't have to hurt anybody. It's very gentle melt, and it's creating our new oceanic crust, basalt. And there are some earthquakes, but they tend to not be very strong there. All right, so we have discussed briefly how our new oceanic crust forms and our mid-ocean ridges, but we did not talk about how the lithospheric mantle there forms. We will do so now, but you do not have to know it for your exam. Okay, so at the mid-ocean ridge, the asthenosphere is upwelling or rising. The lithospheric mantle at the mid-ocean ridge effectively does not exist. So as new oceanic crust moves away from the mid-ocean ridge, the uppermost part of the mantle below it cools, and when it reaches about 1280 degrees Celsius, it's basically going to kind of solidify and fuse onto the bottom of the basalt crust and becomes new oceanic lithosphere. Asthenospheric upwelling. I'd write down the second bullet here. So again, at the mid-ocean ridge, the lithospheric mantle essentially does not exist. And as the plates on either side move apart, the asthenosphere is hot and buoyant. It will rise up. So there is a little story here. The asthenosphere is very close to the surface of the mid-ocean ridge. I don't think we'll have time in this semester to talk about the time that a team of scientists almost successfully drilled down to the asthenosphere near a mid-ocean ridge, but they messed it up. Hotspots. This is our next to last topic for this very long unit. Plate boundaries explain where most earthquakes and volcanoes occur, but not all of them. Sometimes you get, by the way, you need that second bullet there. Sometimes you get volcanoes where you don't expect them, where they have nothing to do with a plate boundary. And these occur at hotspots. So hotspots are fixed thermal mantle plumes. Fixed, meaning they are fixed in space and the plate moves slowly across the top of it. Thermal mantle plumes, meaning they're heat plumes coming from the core mantle boundary. There are as many as 100 hotspots on Earth today. Now, some hotspots are still kicking and some hotspots are dead. And the hotspots can occur anywhere. They can occur on land or at sea. And most of the time, they tend to not happen at plate boundaries, but occasionally they might show up at a plate boundary. I'm going to want you to know an example of a hotspot in an oceanic setting and an example of a hotspot in a continental setting. An example of a hotspot in an oceanic setting would be the Hawaiian Islands out there in the middle of the Pacific. So notice there you have your mantle plume coming up from the core mantle boundary. It will eventually make a surface expression of itself. Now that Pacific plate is moving northwest over top of the hotspot. The hotspot does not move. The plate moves. It's created the Hawaiian Islands. So the only island that has active volcanoes is the Big Island of Hawaii, also known as Hawaii or just the Big Island. All those other islands there, like Maui and Kahulawe and Oahu, those volcanoes are extinct. Why? Because they moved off the hotspots. There's no longer a source of magma. So what we're looking at here is, well, there on top you see the Hawaiian Islands. The ages are listed in millions of years. And then you see the Emperor Seamount, or the Hawaiian Seamounts, and then the Midway Islands. But most important here is the globe image on the bottom left. So both the Hawaiian chain and the Emperor Seamount chain were produced by the same hotspot. Okay, so if we have time to look at this in class and ask you guys about plate movement, we'll do it. But for now, in the interest of saving time, we're going to say, see where it says Detroit? And no, that's not Detroit, Michigan. That's a seamount. 81 million years ago, that part of the Pacific plate was down there where the Big Island is today. So for roughly about 40 million years, the Pacific plate moved due north. And then about 40 million years ago, it torqued a lot and it changed direction quite a good bit. And now it's moving west-northwest. And of course, the only thing here that's still active are the 5 volcanoes making up the Big Island of Hawaii. So this is a nice step-by-step drawing showing there in time 1. You have, active volcanoes being fueled, building islands. But as that plate moves off the hot spot, you're going to end up with the islands becoming smaller. They're going to kind of subside a little bit, and they're not getting bigger, and erosion's acting on them. And so they're going to be smaller islands with extinct volcanoes. And then behind it is the active volcanoes making the new island. And then in time 3, down there towards the bottom, enough time has passed that that one on the far left has eroded below wave base. It's now a seamount. And then behind it, you have a small island with extinct volcanoes. And behind that, you have a bigger island with active volcanoes. So this goes back to the seamounts. When we discovered these with World War II, we could think of them as hotspot tracks. And these are further proof of plate movement. Extra credit question. What is the name of the newest Hawaiian island to be? It's called Loihi. Now, Yellowstone Park is an example of a hotspot in a continental setting, and we can refer to it as a supervolcano. There's a huge magma chamber just 5 miles beneath the park, and we don't have time to watch a video on it. Long before COVID, we ran out of time for that. So here's a drawing of the Yellowstone caldera. So you see that you have this mantle plume beneath that part of the United States, and it's fueling this nice big magma chamber that's only 5 miles beneath the ground. And you have this huge Yellowstone caldera. What's a caldera? We're going to learn what calderas are in the next unit. We'll leave it alone for now. But why do we have all those cool geothermal features in Yellowstone in the middle of a continent, not at a plate boundary? Because we have a hotspot volcano there. And in the white areas, they were reminding us that, well, when you got this hot spot in a continental setting, it's going to stretch the crust and you're going to have some extension. The Yellowstone hotspot track, this is a lot of fun. If we have time to show this in class, we will. I don't know that we will. But anyway, what you see here is on the far right, that red polygon that says 0.6, that's the most recent big eruption 640,000 years ago. And then if you follow that down to the left, you're going to see a yellow polygon at 16.1 million. That's what we found so far today, what we think might be the first eruption there at this particular hotspot volcano. So this is referred to as a hotspot track. So what this tells us is that part of Oregon there that has the 16.1 and the yellow polygon used to be all the way back where Yellowstone currently is today in Wyoming. So this is proof that the North American plate is moving west-southwest slowly away from the mid-Atlantic ridge. Iceland. Potential extra credit question here. I might ask you to know what's special about Iceland. It's a hot spot mantle plume that just happens to be on the mid-Atlantic ridge. Okay, that's the only place where we have an island in the mid-Atlantic ridge, and it has nothing to do with the mid-Atlantic ridge or the volcanism from that. It's because we just happen to have one of these mantle plumes there, making the islands that form the country of Iceland. Here is, this might look like a dried stream channel. It is not. This is just a skinny part of the rift zone in Iceland. Notice the nice dark rock there, basalt. So this is this is a nice image. You've got a drawing there of Iceland. So basically, if you go to Iceland, you're standing on the Mid-Atlantic Ridge. And if you walk across that Rift Valley, you're walking from the North American plate to the Eurasian plate. I think that's really cool. And then in the photo there in the bottom is what it looks like there in the Rift Valley. And because Iceland has, you know, this mantle plume beneath it, they have a geothermal hot spring in Iceland. So this is a map of some of the major hotspots on the planet. Those are shown in the dots. Some are alive, like Yellowstone in Hawaii and Galapagos. Some are dead, like Bermuda. Notice there's 5 in Africa. There's 1 in North America that we know of. It looks like there's none in Eurasia, but I'm betting there's a hotspot somewhere that just hasn't yet made a surface expression of itself. And then the red line is just basically showing the track. So again, these hotspots show us proof of plate movement. Okay, so this is our last topic for this unit, and that's good because it's going to take forever for a 2.5-hour PowerPoint to save. What is the missing mechanism of plate tectonics or continental drift? Well, it's related to mantle convection, so we do have convective flow in the mantle, and especially in the plastically behaving asthenosphere. And of course, Wegener couldn't know about such things. We didn't have the technology yet to figure this out. So once we discovered there was convection in the mantle asthenosphere, we thought that was it. Convection is moving these plates around. We now know that the plates are active players in this plate movement, driving themselves around due to negative buoyancy or gravity. We'll skip this, and we'll skip this, and we'll skip this. Okay, so there are 6 driving forces on the plates, 2 of which are driving the plates around, and then 4 of which are kind of slowing them down. So you only need to know these 2 here, the ridge push force and the slab pull force. And they're labeled on this diagram. So the ridge push force occurs, of course, at a mid-ocean ridge axis. And so you have this isostatic uplift of the ridge axis creating a pressure gradient. So, and again, we might think of it as gravity driven, and that's going to basically very slowly drive the plates apart at the mid-ocean ridge. But the more dominant force here is the slab pull force. This, of course, occurs at your subduction zones, where you have an old, cold, dense oceanic slab sinking either beneath a continental plate or beneath another oceanic plate. And so the slab pull force is basically due to negative buoyancy. It's saying that this old, cold, dense oceanic plate is more dense than the plate it sinks beneath. It's more dense than the asthenosphere. So it's sinking down into the mantle and simply dragging the rest of the plate along behind it. And this one is driven by negative buoyancy. So I am going to want you to know the 2 major driving forces on the plates here, the ridge push force and the slab pull force. I'm going to ask you to know which one is more dominant. That is the slab pull force. And we see evidence for that in the fact that we have faster plate movement at subduction zones by far than we do at the mid-ocean ridges, except for this one little part of the East Pacific rise. Okay, so this is just a little more explanation here about the ridge push force. You don't need to know that last bullet, but it's important, and I like to mention it every semester. Asthenospheric upwelling at the mid-ocean ridge axis is a consequence of seafloor spreading, not the cause of it. In other words, the seafloor or the asthenosphere is not pushing up on the seafloor, causing spreading. The spreading is happening on its own, and then the asthenosphere, because it's hot and buoyant, will simply rise up to fill that void. So the slab pull force, again, just a little more explanation here. That that subducting slab has negative buoyancy, and as it sinks, it's going to pull the rest of the oceanic plate along behind it. Negative buoyancy is strong. Would you want to get on a boat that had negative buoyancy? Gosh, no. Because it would sink, and that's exactly what our subducting slabs do. Okay, so then there's 4 other forces that slow it down. The mantle drag force, the subduction resistance force. You can pause here and read about this if you want to. Here again, you can pause and read about this if you would like to, but two more forces that kind of slow down plate movement, the trench suction force and the transform resistance force. But again, you just need to know the two forces that drive them around, which is the ridge push and the slab pull. Oh, and this drawing here on the bottom where you have a beaker that you tilt at an angle and pour honey into it, and then leave it at an angle and pour water on top, and then set it down flat and watch the honey slowly deform into a flat surface. That's a great analogy for the ridge push force at the Mid-Ocean ridges.